AP Physics students. This is a redo of the lecture we began in class on Friday, February 23rd. It is still Friday, February 23rd, only now it's 4:22 p.m. I fixed some slides, I added some information, but otherwise this is the same lecture you already have hard copy lecture notes for. So we're talking about pendulum. I'm actually not sure what the plural of pendulum is, and how we can model pendulum motion as simple harmonic motion if we take some careful limitations. And then we're also going to talk about damping and resonance. Our textbook does not treat damping and resonance mathematically, only conceptually, and I think that's consistent with AP Physics 1 test guidelines, but I'll check and make sure and get back to you if we need to know more. So, as we discussed already in class, a simple pendulum consists of a mass at the end of a lightweight cord. That mass is usually called the pendulum bob. It's just the name for the thing at the end of the pendulum. And the lightweight cord, we're going to assume, does not stretch and has no noticeable mass. It's essentially massless. If we needed to worry about the mass of the cord, or if we had some kind of, like in a grandfather clock, the sort of stick that the mass hangs on, then we would have to worry about the rotational inertia and rotational properties of that rotating stick. And it's not something we can't do, it's just something that's a step more complicated. So we want to consider what are the forces on the pendulum bob, the mass at the end of the string, and which of those forces or which part of those forces count as the restoring force. So we have to think back to a mass on a spring and how that Hooke's law spring force kept pulling and pushing the mass back to its equilibrium position. Hooke's law spring force, ideal springs, provide a restoring force. And we want to figure out what part or what force involved in this pendulum bob swinging back and forth acts like that. So the forces on a pendulum bob, as it's sort of maybe paused here on the right of its swing. The forces on the pendulum bob are the tension, noted as F subscript T, and the pull of gravity, mg. That pull of gravity has a component. I wasn't going to write this or draw this, but I think I'll draw as I talk as well, just like I did in the lecture. So we have that tension force, and that goes all along the string, right in the direction of the string to the center of, or the axis of rotation. And then we have pull of gravity straight down, mg. So we know that this pendulum is, or the bob, is going to carry out a circular path, or a semicircular path. It's going to move in this circle, sort of defined by the length of the string, as long as the string stays taut. So it makes sense to decompose this weight vector into components that are opposite to the tension and then tangent to the circular path. And you'll have to excuse me, I did not set myself up with enough colored pens. Here, purple, okay? And so the purple vector I've drawn in my picture corresponds to what this diagram, admittedly, on the PowerPoint is a little bit cluttered, but mg sine theta, the pink vector pointing down and to the left. So we want to confirm the angle, our angular displacement of the pendulum bob measured from equilibrium. So where the pendulum would hang straight down when it was not swinging, there's theta. And then here I have a parallel line to that, straight down mg. Here's theta on my string. Here's my string continued theta here. So these are the same angle, theta, theta. So this angle here between vertical weight and the opposite to tension component of weight, we call it like the anti-centripetal, centrifugal component of weight, is theta. So this is mg cosine theta, and purple tangential component of weight is mg sine theta. So as my pendulum swings down to equilibrium position, that angle gets smaller and smaller and smaller, and my tangential component of weight gets smaller and smaller until it's 0 at equilibrium position. But the pendulum at that point has inertia and continues moving to the left, continues swinging to the left. And as it swings up to the left, which you can't see because I guess I could scoop my paper over, right? As it swings up to the left, I develop angle theta from equilibrium again. And now mg sine theta points back to the right. So this is similar to our restoring force of the spring in that my mg sine theta, my tangential component of force, is always pointing back towards equilibrium. Then as I overshoot equilibrium, back towards equilibrium. Then as I overshoot equilibrium, back towards equilibrium. I have a maximum force at the sort of maximum angular displacement. I have 0 force at the equilibrium position and maximum force on the other side at my maximum displacement. So that's really similar to what happened to a mass on a spring, where at equilibrium, we have no force. At maximum displacement, we have kx. Whoops, I don't know why I drew g there, but kx, negative, right? And so this is negative ax, where that's the amplitude, maximum, pulling it back towards equilibrium. At equilibrium, force is 0, but it overshoots equilibrium because it's already got inertia. It then compresses the spring to its maximum compression, which is negative a. And so now F equals negative k negative a, so kx, pointing back towards equilibrium. We have a real similar situation. However, we're expecting F equals negative kx. We've said that in order for this motion to be simple harmonic motion, we should have a restoring force of the form F equals negative something constant times how far you are from equilibrium. We don't quite have that. Here we have F equals, we can put a negative sign in because we indicate when we are displaced to the right, mg sine theta is to the left. When we are displaced to the left, mg sine theta is to the right. So we can put that negative sign there. Mg, that's a constant, that's fine, right? But instead of x, we have this sine theta. And so we started talking about how could we resolve this? It's similar, but it's not the same form. We have this, but we have this. How do we deal with that sine theta? So the key to the dealing with sine theta is that for small angles, for angles less than 10 degrees, and I would even say for angles less than about 15 degrees, sine of theta is pretty close to theta. So if we limit to theta less than or equal to, let's say, 10 degrees, then we're going to say sine of theta is approximately theta. And now we're getting closer, right? Now we're going to say our force is equal to negative mg theta. It's starting to look closer. Negative c times how far you are. Here we have negative mg times angular displacement, but we're still traveling in a linear way here, back and forth. We could stop here and deal with angular sort of notation, but we don't have to. We don't have to, and this is the part I missed in the lecture today. So we have F equals negative mg theta, and it's not quite Hooke's law. But if we remember that this is circular motion, and that the arc length S that I carve out here, the sort of linear position along this curve, if I remember that I can convert from that to angular position, right? This is just from our definition of angle as measured in radians. Then I can use that. Theta must be equal to arc length over r, where r is the radius of our circular path. So in the diagram on the slide, that is indicated as length L. So our final substitution then is F equals negative mg times theta, but instead of theta, we're going to express it as S over R. So S is our position along the arc. R is the radius. Oh, I meant to write that as an L, not as an R. But R is the radius of curvature. Let's rewrite that as negative mg S over L. Now this is the length of the pendulum, which is the length of the radius of curvature. So we can now write our force as negative mg over L. These are things that are constant as the pendulum moves back and forth, times where it is in its circular path. This is equivalent to x. And now we have the force on the pendulum, the restoring force, that is in the same form as Hooke's law, right? Instead of a k, we have mg over L. Instead of x, we have where you are in your circular, archy path. But they're now the same form. So as long as we only consider pendula who are swinging with less than 10 degrees, or about less than 10 or 15 degrees maximum displacement, we can use this force to describe the force that drives that that oscillation, and this is now simple harmonic motion. I think I've got ahead of myself on a slide here, and now I've lost my cursor. Here's what I've been talking about. So since we can identify this quantity mg over L as the equivalent of k, now we remember that we had found that the period of oscillation for a mass on a spring was 2 pi square root of m over k. We now substitute for k here. We substitute this whole quantity mg over L. So we're going to say 2 pi square root of m over mg over L. That's supposed to be L, right? The m's actually cancel. Isn't that odd? So the period of an ideal pendulum, that's where the bob is very massive compared to the string. String has negligible mass, and where you are only allowing the pendulum to swing within about 10 degrees. The period depends only on the length of the pendulum and acceleration due to gravity. So you would only see a change in period if you change the length. It doesn't change if you change the amount of mass. And then, of course, it depends on whether you're on Earth or the moon or somewhere else. On the slide here in the PowerPoint, you've got a whole bunch of other, sort of translations into, or actually, no, there's not a whole bunch of other translations. It's just taking the inverse for the frequency in hertz. So now we'll try some example problems, but I'm going to stop the video and restart.